Go ahead.
Go ahead.
Okay, so I start, yeah?
Yeah.
Okay, so hello everyone. I'm very happy to present our study in collaboration with Gia, actually. So it's some kind of a work in progress. So it's like a preliminary work. So I'm not going to mention it again. So it's like a preliminary. So I'm going to show. And I hope it would be short. No? So it shouldn't take too much. So let's, I hope. Yeah. So what we are doing in heavy ion physics, actually, we all know. So we collide two heavy ions, we produce matters, yeah. So, and then this matter expands and produces our particles, and we detect particles in our detector. No? The way we model, we most of the time separate and divide this evolution in several stages. And each stage, we model them with using, let's say, some phenomenological model or effective theory models. And then we combine these separate models attached to each other in order to explain the whole process. Most of the time, it's very complicated. Now we have a lot of parameters for each of them. So when we accumulate it, when you want to explain everything, you need a lot of free parameters. No? So that's why it makes it hard. But the intuitive picture of the whole process shouldn't be hard that much. So this is the case. We have collision of two ions. We expect to see some kind of environment which is not smooth, no, because the wave function is fluctuating. Therefore, we expect an uniform and symmetric initial state. Now the point is here, if we assume we can apply some kind of a hydrodynamical picture to this initial state, then we can simply see something interesting. Because after the collision, actually we do not expect a lot of momentum in the transverse direction, because most of the momentum is in the longitudinal direction. So if we can apply the hydrodynamic picture, it tells you that okay, we have some kind of hotter or colder parts, or higher pressure, lower pressure parts. Therefore, this complicated shape, I mean, the higher pressure would push itself to the lower pressures. Therefore, this complicated shape somehow gradually during evolution translated into the different, translated into different in the distribution of the momentum, no? And after the expansion, for sure, it's like a quiescent gluons, and we have to produce hydrogen gas. And eventually, what we see in the experiment is particles. If different patches of this system moves with different velocities, then we would expect to see, I mean, more particles in the direction of the velocities. Not one some patches of this initial state turns into particles. Therefore, with this simple picture, we see that if I have some kind of initial state which is not complicated shape, I would expect to see non-uniform and complicated shape, a particle distribution in the end. No? This is some kind of a reflection. This shape is a reflection of the initial state. Okay, so but what is the detail? Of course, as I said in the previous slide, you have to model, and it's completely complicated and very highly nonlinear. No?
So sorry.
Yeah. Can
you go back? Should be initial spatial anisotropy maps on the final momentum anisotropy.
Initial spatial anisotropy, yeah. Yeah, exactly. In here. For those who see later, yeah, it should be a spatial anisotropy. Yeah. Okay, so yeah, so we have as I said, we have initial state and final state. We have to somehow systematically quantify the shapes. No? For instance, for the initial state, we have a two-dimensional distribution. We simply can use moments of distribution, which is in polar coordinates. It looks like this. And for final particles, we can use Fourier series. No? So we can have we can just use the Fourier series, the coefficients of the Fourier expansion, or what we call floor harmonics. But we have another problem, because most of the time it is not possible to really capture the non-uniformity in the final state, because we have not enough statistics. Therefore, we have accumulated many events to have enough statistics, but when you have one accumulated many events, we have the other thing, which means that the particles, I mean, this initial state would fluctuate, so they are not exactly the same shape. One event you have one shape, the other one, so they fluctuate. Therefore, eventually, what you really can measure in experiment is like the statistical properties of this gigantic probability density function. This is what we can do. So you can somehow just concentrate on some corners of it, or just get rid of most of the degrees of freedom. Just concentrate on one. So this is just the two first cumulants of this distribution for one flow amplitude, or you can calculate the correlation between two variables. These are those we actually have access in the final state or in the experiment. Okay, so let me summarize. We have on one side we have theoretical model, on the other side we have experimental data. Theoretical models contain several free parameters we have to fix. We have to just somehow they are inputs. On the other side, we have this distribution of particles most of the time in momentum or in spatial distribution of these particles that we can study. And then somehow we have to connect between these two things in order to understand what's going on in our model. If our model can explain well, or this picture works well, this is we have to connect these two things. No? So of course it's not easy. One way is to just you say, okay, I'm very clever. I can guess the free parameters. This is the free parameters I put in my model, which are most of the time computationally expensive. Now you have to do hydrodynamic calculations. And then you get the final result, and then you compare the final result with your simulations and say, okay, the parameter is good or no, or the model works well or no. But of course, it's not systematic. Fortunately, I mean, in the past years, the global Bayesian analysis is introduced to the heavy ion community. So we can now somehow reverse this process. We can start from measurements, put it to the Bayesian analysis, and then we can infer the parameters. The idea behind it is very simple. Also, we have this just Bayes theorem, which is simple, but of course, the problem are in its details. Also, you have to scan a big parameter space, you have to somehow connect between them. So there are a lot of satellites here. And of course, it needs even more. Of course, you get very insightful information eventually, but it's really, really computationally expensive, no? Because most of the measurements in the final state are correlated. Also, we have very rare initial or observables to say this initial state is merely sensitive to these three parameters. Most of the time they are correlated to each other. Therefore, yeah, so it's not easy really to just compare initial final models. So based on this Bayesian analysis, for instance, the shear and bulk viscosity could be inferred from the measurements before. So what we are going to do here, and we are trying to adjust it. We have practice or exercise to see which parameters in isobar ratios are useful, for instance, to study the initial states. Now, this is what we would like to do. We would like to do. Later, probably we can use this information into Bayesian analysis or apply to hydrodynamic simulations later. So, but for the moment, I'm trying somehow to avoid using hydrodynamic. So let me start with initial state. For initial state, we have again we have several models in the market. What we are going to use here is Trento. Of course, Trento is not, if you say it's very based on the basic principles of physics, it's not. So this is like a phenomenological model, but it's good because we can interpolate between other models now with its parameters. Therefore, and of course, it's really, really fast and easy to manipulate. Therefore, it's very good to use. Also, that's why we just concentrate on Trento model here. In this slide, I try to just briefly explain those parameters I'm using in the next slides. Okay, but I'm not going through the detail, and I just keep some parts. But the idea behind Trento, again, it's not very complicated. You have to choose your favorite nucleus you want to study. Then if this nucleus have some kind of deformation, for instance, it's already discussed before, I guess. So yeah, so we can use this Wood Saxon and then distribute no clones inside nucleus. Yeah, with some randomly you can distribute the no clones inside the nucleus with this constraint. Also, we say actually the no clones cannot be smaller. Their radial distance cannot be smaller than this number. Yeah, this minimum distance between these two. And also after, yeah, so we assume actually each of these no clones, which are distributed inside nucleus, have a Gaussian shape with some widths, no, with W, which is a Gaussian, the width of the Gaussian distribution. Then how can we say if two nucleons can saw each other during a collision? So we have this probability, this probability function, the rho n's, and yeah, they are the density of these rho n's. Sigma g is a fixed parameter. You have to fix this. Sorry, this sigma g should be fixed somehow to get correct cross section for your nucleons in the given center of mass energy. Okay. So as you see, actually, this term is somehow related to the bits of the distribution, bits of the nucleons. So after that, you found how if nucleons actually participated in the collision, then you can add up them with some weight that I'm not going to explain, and to produce this rho, which is the density of the participants. And then because of Lorentz contraction, most of the time we are not interested on the z direction. We just integrate on one and get this thickness function. So we found our participants. Now we should say how these participants actually deposited entropy during the collision. This is the part we introduced this phenomenological let's say function, reduced thickness function, with the parameter p, which tells you how the entropy eventually is deposited into the collision system. If you say, for instance, if send the limit p equal to 0, actually you would get a product of these two a and square root, which mimics for you those initial state models from the IP color class condensate effective theory, like IP class 1. Or for p equal 1, it would be like a Monte Carlo Glauber. Therefore, this p amount also very interesting quantity. So we have these parameters. Actually, I'm not going to talk much about p. I should have somehow removed this p from here. But this is a parameter space I'm trying to explore. No? So, and also the other parameters that we hope to explore later. Okay, so it was the initial state. Now we are going to somehow to see what can we do with the hydrodynamic simulation, hydrodynamic stage or collective evolution stage. So again, with this simple-minded picture, we can say if I have some kind of elliptic shape, ellipticity, so this part should move faster, and whatever happens in this process, I should expect to see more particles in this direction. If I have triangular shape, I would expect to see more particles in this direction, V3. Therefore, here you can see you would expect somehow correlation between epsilon2 and V2, epsilon3 and V3. And if you do the simulation, actually, you see there is a very strong correlation, at least for systems, for large systems. Now, when you have in central collision, for instance, or semi-central collision, you would see very strong correlation between V2 and epsilon2. And also, it's in epsilon.
Can I ask a question?
Yeah.
Okay, so there is a strong correlation as you demonstrate here, but it's not perfect.
It's not perfect.
There is a width. So does that width enter somewhere in your analysis later?
No, actually, I mean, of course, you will see that sometimes. I mean, you will see in the system, in the analysis that it's not perfect every time. So and this is the reason, no, because we have some bits. There are, I mean. For each event, you have different, let's say, quantities, yeah, which are we are blind here. While actually a correct nonlinear hydrodynamic or collective evolution see them. Therefore, and sometimes they're important, of course. Yeah, so this is just some kind of leading approximation, and you always should be careful to use, and always you have to check whether this approximation for your specific observable is working well or no. So
but I mean, you are trying to get rid of the need for doing hydrodynamic simulations because they're expensive. but you are paying the price, and the
Yeah, we are, of
one
course.
part of the
I mean,
price is this uncertainty, and this should be reflected then in the end when you extract
yeah.
information about
Actually,
the initial state in some additional uncertainty.
yeah, sure. I mean, what we are going to present here actually is like to see if the observables are sensitive to specific parameters or no, and later we have to go and do a proper hydrodynamic simulation later.
Yeah, I think it'll be pretty tough to estimate the uncertainty without doing a whole bunch of simulations, right? And I'm not sure it's very easy to just fold it into the analysis. I think you just have to treat this as a first step, and then we're not going to know what the uncertainty is until we do.
Yeah, but other people have done these simulations. You could probably get it from their calculation.
Maybe. I think it requires a lot, though. If you want uncertainty on these like ratios, isobars, and I mean, I think it'll be tricky to get those uncertainties without doing a huge amount of simulations, full simulations.
Okay.
But
actually, it's
not
not
way of doing it better. I don't know. We can talk about it in the discussion.
Yeah. Okay. So let me continue then. So it was like one part of the some, let's say, linear response, and also you can consider the same, more or less same concept with the average momentum. So if you have a large system, so with the same at the fixed entropy. So then if you have a large system, you would expect a smaller PT in the final particles, and if you have more squeezed initial state, again with the same entropy, then you would expect larger PT of particles in the final state. So again, intuitively, one would expect to see some kind of correlation between these two things. I don't know, maybe it's a bit more challenging compared to the previous case. So one can define parameter, I mean, some observable O, then let's say delta O is the deviation from the average, okay? And also a variance like this. It seems actually the best estimator for PT is not like the RMS, actually is the inverse, let's say, the inverse of the area, I mean, the entropy in the unit area, okay? So N part is proportional to the entropy, A is the unit area, and you see, I mean, which is corrected with epsilon2 if you have some kind of elliptic shape. So this deep probably is a better estimator for the or predictor for the PT. Okay. So there are some recipes. For instance, if I have this deviation, you see here, and this relation is not accessible in the experiment because there is no average, and this bracket, this box bracket it means the average PT in single event. Therefore, what we see in the experiment is many event averages. Therefore, you do not see these kind of things. But yeah, we have this linear approximation for a standard deviation. This is what we can use. Also, we can also say, okay, maybe instead of just normalizing with PT, maybe this is also maybe not bad estimator or predictor, which I'm not sure if others also believe it's a good estimator.
The last one I said is not good because
it's not good. Yeah, this is what I also say.
In particular, you know, the mean PT have a lot of have much stronger impact by the, you know, free streaming. All this pre-equilibrium stuff actually contribute to the mean PT, unlike the, you know.
Yeah.
It's the baseline, you know, I mean, you can see they're related. So if you take a derivative, then they are linearly proportional, but the actual values, I think this is not very good.
Yeah. I mean, you will see in the next slide that it's not very good. So we have this some kind of linear relations. Now, why isobar ratios are good? Because we are colliding two ions with same mass, so therefore we expect more or less what's going on in the collective evolution for those apart from the overall geometry. It should be same, no? So whatever this, because these Ks experimentally are not accessible, so we have access on them. We can just estimate them when we have some kind of simulations. We have to do simulations, and okay, and someone is lazy and just do not want to do simulations and just use the other simulations and say, okay, and there are these numbers, and do their job. But if we have this kind of isobar ratio, there is some kind of chance sometimes, at least in some regions, maybe these are really constant, and this linear relation is not that much bad. Then if you calculate these ratios, yeah, so the observables I explained in the two previous slides, then the constant would cancel, and you would expect to directly access to the final states. So in this case, I mean, the linear response should work well, good, no? And of course, the isobar ratios are good, not because, I mean, if there are some kind of sensitivity to the collective part, of course, this sensitivity should be mild, no? I mean, for instance, here in this work, you can see it's AMPT, and you see, I mean, these numbers, you can somehow translate it into the shear viscosity of the system. So it's a kind of collective model. And you see at least the sensitivity on the shear viscosity, or at least this parameter part on cross section, is like not it's very low, no? So the dots are sit on top of each other. Of course, I mean, someone should check for other parameters in collective evolution whether there is no connection or no. But let's say, okay, maybe if you're enough lucky at some points of the parameter space, whether we can cancel these coefficients. Okay, so with that, we go to scanning the parameters. As I said, I mean, it's not like Bayesian analysis to do this sophisticated distributing points in the parameter space and generate events and connect them. So I'm just, I choose my parameter space, which is here, the WD mean, R0, and these parameters. And then at each point, you know, I generate 30 million minimum bias events and get my observables, okay? So as I said, I'm not showing the dependence on P, but of course you can also include more parameters. I mean, if you have a not very big cluster, it's not a big deal. It's not very complicated. So with its setup, yeah. So there is another thing I forgot to say actually, is that the Trento will returns somehow for you the charge multiplicity, because it also fluctuations is included into Trento. Therefore you can get some kind of smooth function for the multiplicity distribution. But of course we do not know how, because we know that this reduced thickness function should be proportional to the entropy, and entropy should be proportional to the charge density, but we do not know the proportionality constant. But it is easy. We have the measurements for ruthenium and zirconium, and then we can just multiply fixed with a number. No, we just can fit this number somehow to get the correct number of multiplicity in the end for separately for zirconium and ruthenium. And then if you just do the ratio, you see that actually the ratio is fitting good with the measurements. I showed just two example in the parameter space, but you should do for each point, you have to do exactly the same thing. Yeah, so we have this, and then we can just look at some results. So this is for, as I said, for nucleus bits and for minimum distance. I choose one specific point in the parameter space. This kind of scanning is, I mean, yeah, they are important for sure, but it's not for the conclusion we are going to do in the next slide. But of course, it's nice to see if our computation is compatible with the other studies. No? So therefore, we check these things. For instance, this ruthenium, which is with ruthenium 4, for instance, is just a simple parameterization. I forgot to say here that we parameterize this ruthenium like this. These are RU96 and ZR96. Those we assume they are the full parameterization for the nucleons deformation, and the other three just we play and change these numbers to see if they are which value of these parameters they are contributing to.
What controls the width of the uncertainty bands in the simulations?
They are just statistical uncertainties. Yeah, so it depends on number of events you generate. This is the only thing, I mean, it is included here.
When you write there V2 ratio, you really epsilon2 ratio because you replace.
Exactly. So this is these are, I mean, exactly. So I'm writing here because the experimental measurements of V2, so they are just epsilon2, and these PET, they are just the perp. No,
I'm asking that for a specific reason. When you go back to your correlation between epsilon2 and V2, you see that they are not strictly correlated, and for every epsilon2, there is a distribution of V2 which I can approximate by a Gaussian, and so there is an uncertainty in that mapping that doesn't drop out in the ratio because you take the ensemble average before you take the ratio. And so that means there should be an additional irreducible uncertainty in your predictions that comes from that variance in between epsilon and V2.
Yeah. As I said, it's always important to check. I mean, for each observable, whether this linear response is working well or no. For instance, here, I mean, I should have put it in the slide from trajectory. Actually, Wietke and his collaborator shows that specifically for V2-2 ratio, which is the most important, let's say, observable for us. For central collisions, like the events larger than 200, So for this case, in their simulation, they have full hydrodynamic simulation with afterburners. They compare the initial state and final state, and they see that actually the ratio would cancel the effect of this, whatever is in this widths in the correlation is not important, at least for central or mid-central collisions. Of course, if we do not know that about this thing, I would say it's not correct to just let's say you should not use it. No, so you have to know it or do it properly with hydrodynamic simulations. Yeah, so we have this. Now we have so this is just one point in parameter space, and then we can go and scan. Okay, so the left part is those that Ulrich maybe say, okay, you're pushing forward, you're using the full range of multiplicity, and you're going to fit what you found to gain some insight, which as you can see, you would expect to see some wrong result. So because the best fit for chi-square, I mean, you just play with this parameter, and what you find is here. So you get very small value for W, and no one else I know could get this thing. And of course, when you go to very central collisions, it's like you see it's very off. No? So it shouldn't be correct. Therefore, here we go to the range that we know the linear hydrodynamic specifically works for V2-2. So in this range, you expect that what we do with this ratio is working well, and then so then you would get a more or less reasonable result. What we would like to see here actually is that how much this quantity V2-2 is sensitive. So because so we know that the numbers we extract in this way shouldn't be taken very seriously. No, so we know, but we can understand from here, because most of the fluctuations origin is coming from the initial state. We would expect somehow this fluctuation, if it is not washed out during the during the expansion, should come from the initial state. Therefore, we can see, for instance, here the chi-square of this region is less than 1, but the other regions you see it grows very fast. Therefore, it can somehow fixes for you, at least for D mean and W. It shouldn't be that much bad. Yeah. So after showing this, let me just animate, just move a little bit if you want to see how these two parameters play and modify the different observables. Yeah. So just I'm not going to talk much more. What I would just say, it seems these observables related to PT fluctuation, I do not see too much difference. Okay, so maybe really the best ones to study, to constrain at least these two parameters should be V22 and V32. Yeah, so let me just go to my last slide and conclude. So what we can say after this study up to now is that the V22 isobar ratio is sensitive to W and D mean initial state parameter. This is what we can say. Okay. And then if you want to trust too much to this linear response hydrodynamic, at least in the central collision, then we can say, okay, it seems this parameter actually prefers W and D mean to be these values. Okay. Or if you just put some range based on your chi-square, it tells you that the D mean should be in this range and it should be in this range, which is not very bad, because from the Bayesian analysis before, we knew that we were getting large W, but in recent studies actually these smaller W's are preferred. And also for D mean, I always see that in Bayesian analysis, the D mean is always very large. The only small D mean I found, maybe you can correct me, is those again the trajectory where you get when you consider this centrality parameter. Then you would get a smaller D mean. At least this study also compatible with the smaller D mean. So in order to understand that,
so if I remember correctly, I think D min is basically not constrained. So it's a little maybe to demand to find the maximum if it's it's like flat.
Very big, yeah, exactly. It's big and flat, yeah. The maximum posteriori was very big, yeah.
Yeah, that's a meaningless number.
Yeah.
That's correct. That's correct. Yeah. So then, so in order to we have to explore more parameters to see if it's effect. Of course, in hydrodynamic calculations needed, no. So in order to increase the power, because we lost lots of beings in the lower centralities, even if we just let's say trust the hydrodynamic linear response.
But even
Thank you.
in hydrodynamics, I'm not sure you can trust the very low in charge region compared to the data, especially.
Okay. So you say even after hydrodynamic, it's not good to trust.
Because for example, I mean, I think I think experimentally probably the non-flow is not the main issue, but I think it's just too many things goes on there, right? Typically, the small region, small in charge region.
Yeah.
Also bar like this, let's say I charge less than 50. I mean,
Okay, so
do we
peripheral
trust?
collisions.
Yeah. Certainly, non-flow will play some role, but it's not an absolute.
Thank you.
We have some time for questions if there's any more.
So Farid,
Yeah.
you were talking about the entropy generation with the TA to the P plus TB to the P over 2 to the root P.
Yeah.
Can you do a Bayesian analysis to see the preferred P values or some different models for this?
I mean, if you say, I mean, we can do the Bayesian analysis to extract P, of course, in Bayesian analysis, P is one of the inputs, of course, and P equals 0 is the most preferred value. Yeah, and
I think it's one of the parameters that's the best constraint. That's correct.
Yeah, it's very well.
It's very well constrained.
But as we heard last week, one can generalize this by writing to the power Q over P.
Yeah, exactly. Yeah.
In order to get in the limit of P equals 0, which seems to be preferred, different possible scalings from root TA TB to 2/3 power of TA TB to TA times TB, and if you include that in the Bayesian analysis, which Goward Nice told us about, I forgot, but I think the Q was not well constrained, or at least he didn't say.
I thought he said it was
It
constrained.
should be because it's the
He
it should control the centrated dependence on the
at least in the previous talk, I remember you wanted to see whether the sort of
But the Q,
CGC thing with the TATB was preferred, or I think he's implied that it's sort of excluded in previous talks. I think he's here if he wants to comment, or at least he was earlier.
yeah, I think he said somewhere in the introduction that 2 power 2/3 is preferable over square root, which would be a Q equals 2, I think, or 2 over P rather than 1 over P. But P is close to 0.
Yeah. I am here.
Yes, go ahead. Go ahead.
I am here, but I have a large delay, so I think I don't know if anyone else is talking right now.
No,
So Q is on average. I think the highest value is something like 4/3 for Q, and then the hello.
Yes.
go ahead.
Keep going.
Keep going.
It's a big delay.
AC Max. Okay, yeah, we will type the answer. That's good. Let's just.
Yeah, typing is probably better.
Any other questions? Okay, so I think we probably can take a break for, oh, no
No,
break.
no,
There's
no.
no break. Okay. Then we will continue and then stop the recording.
No rest for the very.
Thank you, Farid.
You're welcome.